this. So now what do we have? We know all the methods of a class. We're going to know if it's public, if it's private, if it's protected. Later on, we'll look at how we determine inheritance. And this is all coming together. We almost have class diagrams based on this information. And it's all within the binary. We're not, we're not using symbols or anything to extract this out. It's all there. So we can take it a step further and use these class diagrams and generate some kind of UML style graph. I'm not particularly fond of UML, but it has class diagrams. And if someone knows of a good UML library for Python to generate images, let me know after the talk, because I'm really interested in doing that. If not, I could just generate my own graphs. But basically, with all this information, you're gonna have the different, if it's public, private, protected, you're going to be able to tell which variables are private to the class and which ones are accessors, et cetera, et cetera. It's all there. It's all within the binary. And data coupling. Data coupling is interesting too. Let's say you have different objects. Generally, based on the design of the program, you're going to have some objects that work with certain objects and not with other ones. And based on that, let's say that there's some objects that look at network traffic. So there's going to be probably network traffic, and maybe a parser object is going to work closely together. So if you see lots of calls between two different classes, two different object types, you're going to know that those are going to work together. So if you discovered the network stream object, and you see there's this other object that's parsing it, most likely that's not going to be accessed anywhere else. And it's going to give you more insight to how the program is working. You probably want to look at that parser to look for where the data is going, where it's traveling to. So some different implementations. Halvar released a library in Python. I think it's called relib. Most of the library, I think there's 5 files in there. Most of it's about graphing. Splitting up different functions, disassembly to display. There's a little bit of stuff in there for vtable identification. He uses a couple different methods to look for news to try to find constructors and find vtables that way. And there's lots of pretty useful helper functions in there. If you want to find all the cross references to a certain object, it'll create a list for you. If you want to find disassembly for a basic block, lots of useful helper functions. I've used it a bunch. There's also a new article on OpenRCE, which covers a lot of the same stuff that I'm going over here. He wrote some tools in IDC. He does vtable identification and does runtime type identification and some inheritance stuff. I haven't gone through all of it, but you can, the stuff I'm going to show here, you could use any of the methods here, or you could use the methods that I use to find this stuff, and you could use the same code and work the same way. It doesn't matter how you find the vtables or how you find this data. There's just different methods. Each of them is going to have cons. A lot of times when you're doing this kind of stuff, you're going to you're going to find vtables, you're going to miss them. There's going to be mistakes. You're going to have to go back over and verify, but a lot of this stuff is going to make it way easier. So I wanted to use IDaPython, and I wanted to use a debugger with it. The first thing I try to do is extend IDaPython to be able to use the built-in IDA SDK debugger functions. I ran into a problem that IDaPython uses Swig, and I don't know how many people have used Swig, but it's basically like a wrapper class. People use it for Ruby. People use it for Python, for different kind of stuff. And one of the big problems with Swig is it doesn't like variable length arguments like VA list. It doesn't support it. A lot of the debugging functions within the IDA SDK use that to pass arguments, so I couldn't do it that way. So the other solution was I could have some kind of custom marshalling of breakpoint handling, and that just started getting too ugly really fast. So I looked for another solution, and I used PyDebug. PyDebug comes with PyMay. Pedram wrote it. It works really well. Works right out of the box. Does a lot of things that you'd want to do for running a debugger, and it's all there. The code I'm going to show that looks at vtables is very short because of the libraries I'm using take care of a lot of stuff. So this is the algorithm that I've been using to look at indirect calls and cross-references using runtime. So first you find the vtables. There's different methods to find it. You could use one of the ones listed earlier. If you're reversing Microsoft stuff, which most people that are engineering are doing because that's where the money is for vulnerabilities and exploits. And if it's in the standard OS, you're going to have symbols. And with symbols, you know where all the vtables are. The vtable, there's symbols called vtables. Like right here. This is debug help.dll, and it tells you it's a vtable. So there's no work to be done for finding them. So what you're going to do is you're going to set a breakpoint on all the methods in the vtable. When then you write some test code to execute the program, or maybe you just run whatever software it is, and you're going to start hitting those breakpoints as the program's running. Once it hits the breakpoints, it's going to look on the stack and see and figure out who called it, and then it's going to go to that location and create a cross-reference for the function or method that just got called. It calculates sets a cross-reference, and if you want, you can also set a comment into the database so it shows you where it's going. And I'm going to show an example of this. I'll demo an example of this and show you how it works. But basically, this is ideally what we want to do. Excuse me. This is ideally what we want to do. We don't want to see this on the top. We don't want to see EAX plus 14. That tells me nothing. What we want to see is something like that at the bottom, where it says object. And we want to be able to, once we find a function or a method that we're interested in, we want to be able to look at the cross-references and have it tell us this big list of everywhere it's being called from. And let me do a demo real quick and show you how it works. So we looked at this before, this read stream function. And we look at the cross-references right now. All it shows is the vtable. So I'm going to be running this script here. As you can see, most of it is printing out debug stuff, and it's really short. It's like 80 lines long, and this is going to create all the cross-references for us. So all you have to do is highlight your vtable. And then you run the script. Those are all the functions being called. It's done now. Now we can take a look at that read stream function again. And look, this is all the cross-references that we've now determined. So then now we're doing this, right? And so there's one flaw in this right now that let me bring that back up again. But there's one flaw in that right now all we're looking at is execution path, right? It's only what is actually being run. But you can take this, and once you know some of the objects and some of the methods, you start reanalyzing, because a method can call one or two object types. If you trace the registers through, even code paths you don't take, you know what kind of object it is, and you can backtrace and fill that in. So what has to happen now is all these breakpoints you've hit, you store them in a list, and then you reanalyze all the functions that called it, and you start backfilling all this information. And after you do that, you can you start backfilling all these cross-references. Anything that's missing that you don't have there, you could create another and print that out, create a text file or whatnot, or another box within IDA, and then you can go back and try to fill those in. So this is what I'm talking about. You keep on doing this loop, you reanalyze, and then once you do that, you can also take all the locations you don't have data for and try to figure out what runtime path is going to get you there. So you could set breakpoints up until that point, then see how you modify your data to get to the next section, just to get to that code path, and then you start filling in more data. So Keep on doing this process, and pretty soon, you have all the info you need. So this is what I'm talking about. You take your known runtime data and you apply it to the rest of the function. And you keep the list of the cross-references, and you keep analyzing whatever functions and methods you've hit. Something else that is crucial that needs to happen is debugger type info. So I'm sure lots of you used Ollie debug. Let's say a register like this, EAX, and it's pointing to a string. It's automatically going to dereference the pointer and see if it's a string. If it is a string, it prints it out. So why isn't it not doing it for other types of objects? It's only doing it for the string types. So if you have if you have an object, I want it to say my object type. I don't want it to say some random number that I have to try to keep track of, write it down on a little piece of paper, and it changes every time I run it because memory gets allocated different. It's on the heap, so that changes time, right? It has all the information it needs, so I want to be able for it to tell me what type of object it is. I mean, it's silly. So how do we do this? There's a couple different ways. One way is, how about we set breakpoints at every constructor and every destructor, right? So we maintain a list of objects whenever we hit a constructor. We're like, okay, this memory address it's going to return in EAX, because every constructor is going to return the address in EAX. We say, okay, this address is going to be this type of object. And then whenever we see one of those addresses in a register, we say, okay, it's that type of object. So one problem that we run into when we do this is constructor chaining. A lot of times you have an inherited class, and it's going to call the constructor all the way up to the base class. So it called like 5 constructors. What type is it? I guess we'd have to keep track of what the first one was. It starts getting a little bit complicated. Sometimes you call base constructor, sometimes you don't. It depends. That's one way, but it does have problems. Another way is back to our vtables. If you look at an object, the first keyword on it points to the vtable. So we know that has a vtable, so just like looking at a string where it just dereferences and sees if there's a string there, how about we just dereference the pointer and see if that points to a vtable? That has our object, and then we know our type. There's problems with this too. Sometimes when you have inheritance, you might have multiple vtables, but this works good enough. There's always going to be exceptions. There's always going to be problems. I haven't really figured out how I want to do that, if I want to look at multiple vtables or not, but this works right now. So how do we do this? In Ollie debug, I started to reverse Ollie debug to figure out where it does the dereferencing of a string, so I could just hook that function and also try to dereference objects. That's one way to do it. I haven't reversed all of Ollie yet, or at least the parts I need to find that. Within IDA Pro, you can patch the debugger similar to Ollie. All of IDA's executables, plugins, and stuff are all packed with ASPack, and so it's kind of a pain in the ass. You have to unpack it, and then you reverse it, and it's not the same. You're going to see in the it's kind of a pain in the ass. Another thing you could do is just, since IDA uses separate windows anyways for all their stuff, you could just create your own register display that only pops up when you hit a breakpoint or when you step, because you have all those events anyways. So don't use the regular register window. Use the new one, and it's going to display type information. And that's it. It's just an extra plugin. So inheritance. How do we achieve